Hi there, hope you're doing fantastic. This lecture is all about an important topic of mechanics, the conservation of momentum. So in this video, you can look forward to learning about what is center of mass, the position of center of mass, the motion of center of mass, the law of conservation of linear momentum, variable mass, impulse, and collision. So let's get going. First of all, what is center of mass? When we consider the motion of a system of particles, there is one point in it which behaves as though the entire mass of the system, that is the sum of the masses of all the individual particles, is concentrated there, and its motion is the same as would ensue if the resultant of all the forces acting on all the particles were applied directly to it. So this point is called the center of mass, or COM, as I would refer to it in the upcoming slides of the system. The concept of center of mass is very useful in solving many problems, in particular those concerned with the collision of particles. So to put it in a nutshell, the center of mass of a body or a system of particles is defined as a single point at which the whole mass of the body or system is imagined to be concentrated and all the applied forces acts at that point. Yes? So the problem is many get confused between the center of mass and the center of gravity, but they are essentially different. The two terms are so similar in many respects that one can use the two interchangeably. The center of gravity of an extended object coincides with its center of mass if the object is in a completely uniform gravitational field. If the body is not located in a uniform gravitational field, its center of mass and center of gravity will be at two different locations. Let's have these images as examples. The first image has a body, a rigid body, which is placed in a uniform gravitational field. So you can see the center of mass and the center of gravity coinciding at a point. Whereas on the other hand, in the second image, the body is kept in a non-uniform gravitational field. And so you can see the position of center of mass is essentially different from that of the center of gravity. So be clear, don't get confused between the center of mass and the center of gravity. So make sure you are aware of what type of gravitational field the body is in. Now moving on to the next topic is position of center of mass. First of all, we find the position of center of mass of a system of particles. Just to make the subject easy, we classify a system of particles into three groups: system of two particles, system of a large number of particles, and continuous bodies. Now let us take them separately. First one is the position of center of mass of two particles. Center of mass of two particles of mass m1 and mass m2 separated by a distance d lies in between the two particles. The distance of center of mass from any of the particle r is inversely proportional to the mass of the particle m, and that's why we have got this equation: r is inversely proportional to the mass of the particle. So this can be written as r1 by r2 equals m2 by m1, which is nothing but m1 r1 equals m2 r2. So solving these two equations, we get r1 equals m2 by m1 plus m2 into d, and r2 equals m1 by m1 plus m2 into d. Here r1 is the distance of center of mass from m1, and r2 is the distance of center of mass from m2. From the above discussion, we see that r1 equals r2 equals d by 2 if mass m1 equals m2. That is, center of mass lies midway between the two particles of equal masses. If r1 is greater than r2, it implies that m1 is less than m2, and r1 is less than r2 when m1 is greater than m2. That is, the center of mass is nearer to the particle having larger mass. So now we'll move on to the next topic, that is position of center of mass of a large number of particles. If we have a system consisting of n particles of mass m1, m2, m3 and so on till mn, and r1, r2 and so on till rn bar will be their position vectors at a given instant of time. The position vector rcom of the center of mass of the system at that instant is given by this equation. That is, the position vector of the center of mass equals the summation of the mass times the position vector of individual particles divided by the summation of the masses of the individual particles. So we get summation of mi ri bar divided by summation mi. So the denominator becomes capital M, which is nothing but the total mass of the individual particles. It is also to be noted that this term in the numerator, that is MIRI, is called the first moment of, summation of MIRI is called the first moment of the mass. Further, if you take vector R to be equal to the different components, say xi I cap plus yi j cap plus zi k cap, then the center of mass, the position of center of mass can also be written as x com I cap plus y com j cap and z com k cap. So the Cartesian coordinates of the center of mass can also be calculated in a similar fashion. So all you have to do is replace rcom with the required coordinate. If you want the x coordinate of the center of mass, place m1 x1 plus m2 x2 and so on till mn xn. And if you want the y or the z coordinate of the center of mass, replace r1 by the y or corresponding z coordinate of individual particles. And that's how you'll get the Cartesian coordinates of the center of mass. So now we'll move on to the next topic, position of center of mass of continuous bodies. If we consider the body to have continuous distribution of matter, the summation is the formula of in the formula of center of mass is replaced by integration. Suppose x, y and z are the coordinates of a small element of mass dm. We write the coordinates of center of mass as x com equals integral x dm by integral dm, which is nothing but integral x dm by capital M, that is the total mass of the rigid body. Similarly, we get the y coordinate of the center of mass by integrating, and again the z coordinate of the center of mass. Now you take an exercise of calculating the center of mass of a uniform rod. So you must be able to find the answer through the similar means of integration. Now we'll see the center of mass of some well-known rigid bodies. Center of mass of a uniform rectangle, a uniform square or a uniform circular plate always lies at the center. Center of mass of a uniform semicircular ring in the first diagram lies at a distance of h equals 2r by pi from its center on the axis of symmetry, where r is the radius of the ring. The center of mass of a uniform semicircular disc, this diagram, the second diagram, of radius r lies at a distance of h equals 4r by 3 pi from the center on the axis of symmetry. The center of mass of a hemispherical shell in this diagram of radius r lies at a distance of h equals r by 2 from its center on the axis of symmetry. The center of mass of a solid hemisphere of radius r lies at a distance of h equals 3r by 8 from the center on the axis of symmetry. So these are the results, the position of center of mass of some well-known rigid bodies. I suggest you to remember these things by heart. So this will be of immense use when you solve the problems involving the center of mass or the position of center of mass essentially. So now we'll move on to the next section, which is the motion of center of mass. Let us consider the motion of a system of n particles first, of individual masses, say m1, m2, m3 and so on till mn, and the total mass capital M. It is assumed that no mass enters or leaves the system during its motion, so that m remains constant. Then as we have seen, we have the relation, the position vector of the center of mass. I'm sorry, here I have forgot to make this as the vector notation. This is actually the position vector of the center of mass. So this equals the summation of the masses, the product of the masses and the corresponding position vector of individual particles divided by the total mass. Now, taking this m to the LHS, we get m RCOM equals summation of the product of the individual masses and the position vector of the particles, which is nothing but the first moment. Now, differentiating this expression with respect to time, we get this expression, that is m into dRCOM by dt equals m1 times dR1 by dt plus m2 times dR2 by dt and so on till mn times dRn by dt. You all know that dr by dt is nothing but velocity, that is the rate of change of a position vector. So now replacing this this term dr by dt with velocity, we have mvcom equals m1 summation of the mass of an individual particle with the velocity of the individual particle. So we'll get the velocity of the center of mass to be vcom equals summation of mi vi bar by the total mass m. Further, you all know that mv is nothing but the momentum of a particle, which is vector p. Therefore, equation 1, which is this equation can be written as pcom equals p1 plus p2 plus p3 and so on till pn. Now the momentum of the center of mass is nothing but the summation of momentum of the individual particles. Now differentiating the first equation, that is this equation with respect to time, I'm sorry, differentiating this expression with respect to time, we get this equation, that is m dvcom by dt equals m1 times dv1 by dt plus m2 times dv2 by dt and so on till mn times dvn by dt. So dv by dt is nothing but acceleration. It is the rate of change of velocity. So m into the acceleration of center of mass is nothing but the summation of the product of mass and acceleration of individual particles. So now we get the acceleration of center of mass to be equal to the summation of the mass of a particle multiplied by its acceleration divided by the total mass m. So this is nothing but the acceleration of center of mass equals summation of mi ai bar divided by total mass m. Further, in accordance with Newton's second law of motion, we all know that F bar equals m a bar. Hence, we can use this here in this expression. So we'll get, from this equation, we'll get FCOM, that is the force acting at the center of mass, equals F1 plus F2 plus F3 and so on till Fn. So the force acting on the center of mass is nothing but the summation of forces acting at the individual particles, and that's why we have FCOM equals summation Fi. Thus, as pointed out earlier also, the center of mass of a system of particles moves as though it were a particle of mass equal to that of the whole system, with all the external forces acting directly on it. So now we have some important point to discuss. Students are often confused over the problems of center of mass. They cannot answer even the basic question of COM. For example, let us take a simple problem. Two particles, one of mass 1 kg and the other of 2 kg are projected simultaneously with the same speed from the roof of a tower, the one of mass 1 kg vertically upwards and the other vertically downwards. What is the acceleration of the center of mass of the two particles? When asked this question, students generally offer three answers: g, g by 3 and 0. But the correct answer is g, because we all know that the acceleration of center of mass is nothing but the summation of the product of mass and acceleration of individual particles by the total mass. From this expression we get ACOM equals m1a1 plus m2a2 by m1 plus m2, since only two particles are involved here. We all know that the acceleration here is the acceleration due to gravity, which essentially acts downwards for both the particles. So a1 vector equals a2 vector equals g. So we have ACOM being equal to 1 into g, that is mass of the first particle is 1. So 1 into g plus 2 into g by 1 plus 2. We'll get 3g by 3, that is nothing but g. So don't get confused. The idea behind this is that apply the basic equations when asked anything about center of mass. So now we'll move on to the next section, which is the law of conservation of linear momentum. The product of mass and the velocity of a particle is defined as its linear momentum vector p. So we have vector p equals m v vector. The magnitude of linear momentum may be written as p equals mv. Now squaring it on both the sides, we get p square equals m square v square, and now multiplying and dividing by 2, we have 2m into half mv square. We all know that this term is kinetic energy, which can be represented here as k, so we'll get 2mk. Now the momentum equals under root 2 times the kinetic energy and the mass. Now the kinetic energy equals p square by 2m. Now in accordance with the Newton's second law, we have force equals ma. So a is nothing but the rate of change of velocity, so I write this as m dv by dt. Now taking m inside the derivative, since it is a scalar here, we have d mv by dt. So mv is nothing but the momentum, so we have dp bar by dt. So F is nothing but dp by dt. In other words, I should say force is the rate of change of momentum. In case the external force applied to a particle or a body be 0, we have F equals dp by dt equals 0. So the differentiation of p with respect to t equals 0 means p is a constant. So when this shows that in the absence of an external force, the linear momentum of a particle or the body remains constant. This is called the law of conservation of linear momentum. The law may be extended to a system of particles or to the center of mass of system of particles. If the net force or the vector sum of all the forces on a system of particles is 0, the vector sum of the linear momentum of all particles remain conserved. Or I can say it as when F equals F1 plus F2 plus F3 and so on till Fn, this equals 0, then P1 plus P2 plus P3 and so on till Pn equals a constant. The same is the case for the center of mass of system of particles. That is, if the center of force acting on the center of mass FCOM equals 0, then PCOM, that is the linear momentum of the center of mass, is essentially a constant. Thus the law of conservation of linear momentum can be applied to a single particle, to a system of particles, or even to the center of mass of the particles. The law of conservation of linear momentum enables us to solve a number of problems which cannot otherwise be solved by a straight application of the relation F equals ma. For example, suppose a particle of mass m, initially at rest, suddenly explodes into two fragments. Just imagine the scenario. I cannot support this with an image here, I'm sorry about that. Just imagine this scenario. A particle of mass m, initially at rest, suddenly explodes into two fragments into masses m1 and m2, which fly apart with velocities v1 bar and v2 bar respectively. Obviously, the force resulting in the explosion of the particle must be internal forces, since no external force has been applied. In the absence of external forces, therefore, the momentum must remain conserved, and we should have mv equals m1 v1 plus m2 v2. Since the particle is initially at rest, v, that is the initial velocity, is 0, and therefore m1 plus m1 v1 plus m2 v2 equals 0, from which we get v1 equals minus m2 by m1 times v2 bar, or mod v1 bar by mod v2 bar equals m2 by m1, showing at once that the velocities of the two fragments must be inversely proportional to their masses and in opposite directions along the same line. This result could not possibly be arrived from the relation F equals ma. Since we know nothing about the forces that are acting during the explosion, nor could we derive it from the law of conservation of energy. So this is pretty much about it. We'll see about the variable mass, impulse and collision in the upcoming videos. Until then, see you all and practice problems based on the position of center of mass, motion of center of mass, and also based on the law of conservation of linear momentum. And don't forget to solve the exercise that I have given. Try to find the position of center of mass of a uniform cylindrical rod. Yeah. See you.